So at this stage, what I want you to do is you turn on your, if you haven't already done, you turn on your R Studio because we are going to do the analysis. Now, why do I normally like the R Studio to be used? I like it because it can do a lot of DEA variants. You can use it to do a lot of the variants, but also it's free. It's free. Now, there is a package which is known as Efficiency Management System. If you just type Efficiency Management System, it's an old package. Jerry, I hope you are not disturbing us. It's an old package, and if you let me just type DEA. So that's it here. It's quite an old package. But one of the things it used to be very good at is the estimate. You can see that it's a very old one. It is very good at estimating MAMQuest productivity, holding some portions of the frontier, meta-frontier analysis, and all of that. So this is a web page for that. Just know it. Know it, because sometimes it's just good and important that you know that the thing exists. So you can see it there in your chat here and know it. Another one is a Max DEA, very, very powerful. The only problem with that one is that you need to buy it. Emily, you used a Max DEA before?
No.
You should. I have a version I think I have bought, and I just need to upgrade that version. But it's a very powerful version. Very, very powerful. Because it does so many things. So when you go here, you can only get a version for, for example, if you download this version, the good thing is that it is limited to the basic models, DEA, SBM, cost, revenue, basic. And you have up to 1,000 observations. Now that is good. So it means that you can still use it, but there are some portions that are not available. Then there is a purchased one, okay? And it's always good to go for the academic purpose one. The academic purpose, if you want to have one that deal with 1,000 rows, is $360. Other than that, 100,000 and beyond. So let's focus on the $360. Now, one interesting thing is that you can only install it on one computer. You see, it says here, transfer the license to a new computer. So suppose you use it on this computer and this computer is spoiled and you want to transfer it to another. You can't unless you email. So it says here, after payment, you will now send the filled order form to Chen, and he will give you the license code, because anytime you open it, it will require a license code. Okay. And they will respond very quickly and give you the license code. If you get any information within 24 hours after you place your order, please check your spam. And then according to them, we suggest you add your email list, their email to your safe list. But here's a key point. If you want to use a new laptop, the license is for one computer only. It's not permitted to use it on a new computer at most twice per year. Get a point? So it means that if you want to change your computer, and your computer spoils, then you change it to another computer. That spoils. Okay. You have one more computer within this year to use it. In other words, and by the way, you can't use it on two computers at the same time. But even though you are going to use it on different computers, it will deactivate automatically on the previous computer, so you can use it on the new computer. But even that, you can't use more than two computers. Does that make sense, guys? What does that mean?
Yes, it does. That effectively only the software can only run on one computer at any given point in time. So even if you installed it on multiple devices, it will only be active on one.
Exactly. And it's not like when you stop using it, this one, you can go back and use it on the other one. No, you can't. For at each time, you have to now ask for a code to use it on a computer. And you can't ask for that more than twice. That's the whole point. Okay. The license on the old computer is always automatically disabled. It's very powerful. Let me tell you some of the things it does that makes it powerful. When you go to this home page and the comprehensive DEA models here, it does all of that. Okay. So envelopment model, multiplier model, you can run it. You can get the scores you can do free disposal haul. You can do both the BCC and CCR, the variable and constant returns. You can look at the enhanced Russell measure, the tone SBM, okay, and then the expansions of them, the minimum distance is a strong frontier, and the papers that develop some of those, you get them under all kinds of orientation. We can do the usual directional distance function and then different directional vectors. You have directional vectors all the way up to 12. Those that are customized and those that are not customized. You can have the range directional measure by patella. Okay. You can have a series of weighted additive models. Several of them, including the range adjusted, the banded adjusted, and even the directional slack one by Fukuyama and Weber. You can have all of that. You can have the hybrid, both the radial and the SBM measure. It's very good. It has some advantages and disadvantages. You can do the tone and chichi, the dynamic efficiency one. You can do cost, you can do revenue. There are several orientations you can use. And these are click, so it's good. You can do different kinds of retention scale. The one that it will actually produce the retention scale. And you can do these kinds of retention scale under both efficiency and productivity. I just wanted to know how powerful it is. You can do total factor productivity, Malmquist and Higgs-Munstein, either of them. The adjacent Malmquist you can do. The base period Malmquist is also there. The global Malmquist is there, by, what do you call it? Fair. The global Malmquist. The biennial Malmquist is also there. The sequential Malmquist is there. All of these, the global with sequential is also there to do it. And in all of these Malmquists, you can decompose it into efficiency, technological, skill, bias technical, and all of the different kinds of. You can do cross efficiency, okay, and you can use fixed benchmarking. And you can do super efficiency, modified SBM by different people. You can do the second stage models. All of these new models are also there. You can do game cross efficiency that employs a Nash equilibrium. You can incorporate desirable and undesirable outputs, discretionary and non-discretionary, weight restrictions. Can either do the cone restricted. There are different kinds of weight restrictions. So all of this you can do. And then he says that it provides almost all combinations of the above. So if you can, and why do I normally suggest that you use it? Because sometimes you want to let your results from the R square, from the R software, you want to make sure that your results tally, especially for your hypothetical data. So you want to be sure. All of you are going to do hypothetical data, so it's important that you do this. So whatever the R studio is going to give you, you want to be sure that it's the same here, so that when the need ever arises, you know that you're on the right track. All right. Now let's go to the R studio. So this is the R studio. We want to start first by looking at, so these are the main softwares. These are the softwares, but the key ones are the ones we just. Now, I must also put it across that there are two key softwares you want to note, especially when you're developing a new model altogether. Like you, Emily, you know, all of you who are doing MEA, dynamic MEA, cost MEA, these are new. And those ones will require that you develop the models and the code yourself. You merge a couple of codes. Now, Lingo can do that for you. Lingo is a purpose-driven, and it can also allow you, of course, the R can do, but Lingo can let you combine codes. MATLAB is also there, can let you combine code. The key point is know three of them. Know at least three of them. So that will be R, okay, Math DEA, and then Lingo. That's it. So we're going to start a bit of information because R is works better with matrices. That's the one we are going to be using. And there are some keywords you got to note when it comes to R. For example, you can concatenate matrices. You can add and split matrices to create larger ones. Okay. So why R? R because a lot of people like it. There's a big community. It's free. It's a hottest trend. It has platforms that are independent, and you can integrate it with other softwares. So go and take the codes I've given you, and I know you have them. We're going to start showing some bit of things. Okay. So we are going to deal with two columns of two matrices with the same number of rows. And those two matrices, columns, can be combined into a larger matrix. So when you look here, you have a matrix which is B. Now, the number of rows at the end here and the number of columns at it will tell you that the thing is how many rows and how many columns. So, give you what I'm showing here. If you were to run this, and I know you're yet to do it, but don't do it. If you were to run this, how would the things be organized? If you were to run it, how will it be organized? The numbers are put together. So how would they look like?
Doc,
Jerry, go ahead.
that's going to be 2, 4, first row, 3, 1, second row, 5, 7, third row.
Very good. Excellent. So let's run this command and see what he said. Okay. Oh. Click here, and then I'll go and show the B. So highlight the B and show. And you see that it is showing at the bottom exactly as he said. Okay, what about the second one? And you should be doing the same thing I'm doing. What about the second one? That one is obvious. Okay, because there are 3 rows, 1 column. So the whole thing is going to be from 7 going downwards. And that, when you run it, you're going to get to this when you show the results. Are you guys running them?
Yes, Doc.
Yeah.
Okay. Now, let's column bind. Okay. We are going to column bind. We are going to combine the columns of B and C. And we are doing that using the column bind, C bind. So we're going to C bind. It's just like you're adding them together. Okay. We're going to do that. So when you do that, you get this. You're just adding the column C to the matrix C to the matrix B. Now let's create another matrix. And this time it's a D. Okay. Now when you check matrix D, you know that when you show the results, it's just showing 6 and 2. And so given this B up there, we can combine the B and the C. But how are you combining them? We are using a row bind. So we are combining the rows of these two matrices. But you see, you can only combine the rows if they have the same column numbers. Okay. If they have the same, then you can now go and do the row bind. And they have, okay, they have the same, column. When you check, for example, B up here, you see that you got, 2 columns there. 2 columns there. And then when you check D, it's got 2 columns. So we can now do a row bind of them. So when you do the row bind, you're going to get something like, because you're just, again, adding it to it. Just as you topped up the columns with a C, you are topping up the rows with a D. Okay. And then finally, you can also have a complete data set brought in to the R. And so this plant growth is a typical data set, as you can see. You have groups on the right, you have weight on the left. Okay. Now, when you check the control, it looks like control, but it's not. This is, you see, it has several names, plant growth types. So normally, if you want to have exactly what it is, it will give you some bit of information, but this very one says there is no documentation for the plant growth topic. Let me see whether, no, there is no documentation for it. But sometimes you will get a bit of a documentation about the thing that you want to really, really deal with. But in other words, you cannot get lost, because even ChatGPT can give you some bit of information that you want at any point in time. So you don't have to be worried about. But this data set is a very important thing, because it talks about the dry weight of plant, which is in the numbers, and then the treatment group, the factors. So the first one here, the CT, blah, 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 is a control group. Then you have the treatment group 1, treatment group 2. Okay. So those are the plant growths. Now you can look at the head of the plant growth. For example, you can just type that. Let's look at the head. Oops. Let's click and look at not even the head. I mean, you can look at the summary. So you can just type summary, and then you select. And then you type the plant growth. When you start typing, it will show. So it will give you a bit of a summary of the things you want. And you can see that it tells you that there are 10, 10, 10, 10, 10 in each group. Okay. Now, the most important thing is that for the basic DEA analysis, you are going to use benchmarking for it. Remember, to work with the DEA, it's best to use data frame. And a data frame is just a combination of the features of a matrices and a list. Very rectangular list. Okay. And that was a plant growth. An example is a plant growth that we just did. Please note that a matrix doesn't have names. but a data frame have got column names and row names. Take note. So if you look at the data frame that we have here, we have column names. So if you go back to plants, we have column names. Okay. The column names are weight and the group. And then the row names are the 1, 2, 3, which are automated there. All right. So now we are going to go into our data set. The very data set we had in Excel. And we are going to copy the data set into that. So please get back to your Excel. You remember this data set? Do you remember you drew the graph? Do you remember?
Yes, Doc.
Yes.
So we are going to load the data set into Excel. So please load the data set from Excel to R. Load the data set from Excel to R. I mean, you all have it, so just go and
Doc, should we include the normalized data? Because in the class we had the normalized one as part of it.
yes. When you say include, you mean should you include the one that Y was 1, 1, 1, 1, 1?
Yeah.
Yes, that's the one we are dealing with. Let me show you. So this is the data, the yellow one.
Okay.
So you see, you copy. Remember that the way you label the DMU names, if they are capital, make it capital, like I have. Okay, take it to your R Studio. And we are going to give it a name. We are going to load it using the clipboard. And we are going to call it Farm1. There's a reason why. You see, all of these things I'm showing you, but ideally you would have coded them yourself. I wrote all of them from memory. At that time, ChatGPT wasn't even the case. So I renamed it as Farm1. Okay. And I load it. The data has been loaded. To show that the data has been loaded, I will just run the next command, which is Farm1. And now at the bottom here, you see that the data has been truly loaded. Let me see who has been able to load his data and can see the results like mine. Albert. Who else? Who else has been able to load the data?
Doc, I'm typing. I'm now typing.
Who else? After that, we are going to install a package because you always need to have this package before you can do proper descriptive statistics. There are several ways of loading the data. I use the clipboard approach. Now, the reason why I brought the descriptive statistics because you got to do all of this in a normal work. Everything from data pre-processing, data wrangling, all of those got to be done before you go to the estimation of the DEA. So, because you'll be doing a similar one with your work. So if I load the library past the psych, if you don't have it, you have to install it first. If I load the library psych, and then do a description of the Farm 1 data, you get something like this. And of course, it tells you which ones, these are the various descriptive statistics that one may need. So you can see clearly that DMU names are non-numeric. They are non-numeric. Okay. Now, the most important thing is the next command we are going to do. If you are lost, you got to mention it. Now, you see, I have created a code known as farm equal to farm 1. And then I've said that convert the column, that's a DMU name, inside a data frame into row name. Now, this is powerful. Why is it powerful? It's powerful because now what you are going to do is that you are creating a new data frame called farm. And that new data frame, you are removing everything in the second column. You are only keeping things in the first column. The second, sorry, yes, you are removing everything in the second, then the other columns, keeping everything in the first column. You are removing what is in the first column. If you check the data set called farm, okay, the one called farm 1 here, you will notice that the first column is DMU name. And that column, you are removing it. That's what this command will do. It will remove it. The next command will replace the row name of the first column with the row name of the farm. Okay. And then this one will show the farm. And then the next command will now call the names in the new farm. Okay, so the new farm, we are going to rename it. Farm 1, the new farm 1. I called it farm after removing the row names. And I come and then request for the row names. I said that now replace whatever row names inside this one, replace it with the row names of the row. So you see that the row, you have number 1, number 2. You're going to replace the number 1 with DME1. You're going to replace the number 2 with DME2. And then number 5 with DME5. That's what you're going to do for this command. So after doing the row names, now you can check the results. You can see exactly the results here. So what do you see between the results here and the one before? What do you see? Anybody?
So the first column is gone and it's been replaced with the DMUs.
Why do you think we are doing that?
I think so that once we call out a specific DMU, so rather than using just say 1, 2, we can refer to that specific row with the name of the actual DMU.
Excellent. But there's another reason why we are coming to. Who knows? Why are we doing that? There's another bigger reason why. It's the fact that when we come to the drawing, we don't want the software to use 1, 2, 3, and then on to represent the name of the DMU. Because it will always use the row name to represent the name of the DMU. But right now, the row name is 1, 2, 5. So if we replace the row names with DMU1, DMU2, DMU5, then it is when it is drawing, that's what it's going to use to label the graph. Please, do you get me?
Yes, Doc.
Very good. So we now go ahead and then we show clearly the information. So that is what we have here. If you want to now know the names of the new data, when you click names, okay, the column names, you are getting X1 and X2 and Y, just as we want. Okay, but now we are going to now column bind the X's. So you see all the X's, even if the X's were 12, we can create a complete matrix of all the inputs. And that's what we're going to do. So all the inputs, which are X1 and X2, we are going to call them what? X. And then all the outputs that are Y1, Y2, Y3, Y4, whatever Y, we combine it all into Y. So let's do that one. And in fact, I will show for each for you to see. So for the input, now we have this on the bottom. And then for the outputs, you run it, and now you have Y as the output. Okay. You can do the same thing for the input prices. But why are we not doing that now?
That's because that one is useful for cost efficiency rather.
Exactly. So if you are estimating cost efficiency, which we will, that is what you'll be dealing with. Okay. So I'm jumping the W and co. And now the next one, I'm just going to write for purposes of graph only. For graph purposes only. It's important you're always giving a couple of instructions. Why are we saying for graph purposes only? For what we're about to do. Why are we talking about that? Because when we start going to the graph, we are going to represent the graph as X2 graph, okay? It's going to be something like, and then X1 graph. So we got to pull out from this new data. That's why we are doing that from the family data frame. Can you fish out X1 representing the column for the X1? The reason why you got to do this is that sometimes you don't have the full name. So let's say that you have labor, you have capital, you have several things. You will say that let all of them be X1. Okay, let all of them be X1. And then let all of them be X2. So you change the X1 and the X2 for each of them. At first it was for one of them, but now it becomes for each of them. So that's how you estimate this very example. Okay. Any question on that before I proceed? So if you check this, I'm going to rename this X1 inside a farm data set and X2 inside a farm data set, like I've just done. It normalizes the output. And so you are using the normalized output here. All the codes are implicit. We are automatically assuming constant returns to scale because we have not identified. This is going to estimate the efficiency of each firm one at a time at the speed of light. Okay, so let's start the installation process. For that to be done, you need to invoke a package called library. Invoke it now. Install a package called library.
That is the benchmarking.
Sorry?
Is it a library bench?
Is it a what?
Library benchmarking.
Yeah, have you all installed and then libraried it?
Yes, I have.
No, when you install it, we have already installed it as a package. We have to
Just liberate like I've just done in my command 38. Just liberate. After that, you're going to do the first plot. Pay attention to the code. The plot says, let us plot x1 and x2. Let's call it purple. The line width should be 2. Okay. The positioning should be 8. And which part of the data point should it be labeled at? Which part of the data point will it be? And that is a CEX. Then the true here means you want a text. The main is the title of your graph. The true here means you want a text to appear. So we're going to run this first command. And you can see on the right that it has scatter plotted the data point for all the 3 DMs, all the 5 DMs. It scatter plotted the entire data set. Okay. Now, watch it. The other thing is you will do, so this is the first one. The second one, I'm changing some of the symbols. So the second one, you see that I've used a PCH to be 5. I've increased it. The text is true, and the other ones will remain as it is. Let's run the second one. Okay. It also gives us a different scatter plot of the data. And from this scatter plot, you can draw your radial lines, can't you? Now, you can do both orientation. Okay, you can do constant and variable tensor, but this one, you cannot do the type of orientation in this version. Why? The orientation.
That means you can't do the orientation because it's both inputs.
Because what?
Since they are both inputs, you cannot do output orientation here as well as the non-orientation.
Okay. So we are going to do the plotting. The plotting. Okay. And if you check the color, you can see it, right? So let's do the plots. Okay. So there's another plot. I'm just showing different colors. Now, when you see the difference between this plot and the previous ones, what you see is a difference between this one and the previous one. Apart from the fact that we are using a times in this example, apart from that, what other thing do you observe? What other thing do you see?
Okay, each DMU seems to have a different color.
That's the point. So you can see that at the end, I indicated what color. Watch it. I said the first one should be given a blue, second is red, okay, and then on and on and on. So technically, it allows you to also know which one is the first. Which one is the first? Okay, so keep this in mind. Now let's go to the estimation of the radial line. Okay. Or let's start with the frontier. The frontier first. Because that's the first thing. That's the code 47 here. For you to be able to do that, you have to indicate the orientation. This is an input orientation, the retention scale. This is a constant retention scale. Okay. And the line weight, the PCA, the CX, all of them are shown here. Let me ask a question. Can we change the orientation to be output oriented? Can we change the orientation to be output oriented?
Okay, yes, we can.
Yes, we can. When you look at this thing very carefully, if you were to do the output oriented, which DMU color, which color DMU will be on the frontier?
Then can you please add the names so that we can use the names to say?
No, that's what I'm saying color for now. Let's use color or color.
Okay, so for output, I think DMU one, which is the blue. Yeah, it's
Use
blue.
color, na free la.
Then for output orientation, we are going to have good, yeah, I think blue and green. Yeah, that's main orientation.
So you have the first top blue.
Right.
When you say blue and green, you have to be clear. The top blue. Because the blues are two, right?
Yes, the top blue, and then the green, and finally the blue again.
Okay. Now let me use a different color for what do you call it? For the last one. Because there are 5 DMUs. So I'm going to add
Pink.
I'm going to add another color here. So let's use a color. Which color should I do?
The pink is okay.
What?
I said pink.
What color is that?
Pink.
Ah, pink. Oh, I forgot we have a lady. So yes, you can see a beautiful pink color. Let me bring that here with what we're about to do. You should also edit it. Okay. Let me run it again. So you can see the pink. You see me, I knew it wasn't going to be so beautiful. But we have a girly. So we need to respect the girly. Okay. So we have these colors right now. Now let's go to the frontier. Command 47. You see the frontier. This is a DEA frontier. Ben Susan, are you with us?
Oh, yes, Doc, I'm here.
Have you done it?
Yes, Doc.
Okay. Whoever has not done it and needs help, say it.
Doc, I got some errors along the line.
There's a spelling. I've put it on the page. I've put the code on the page. So if you got a mistake, it means that your spellings, there's some problem with the spellings. What is the error? Okay. So now we've been
Doc,
able to,
yes. Okay, sorry. Oh, it was telling me about some dimension issues along the line.
But you still got the
Data
thing.
frame,
You still
undefined
got it
colors.
drawn, didn't you?
Yes.
Okay. If
No,
you got
I've
it.
not done. I'm yet to draw it here.
Now, the command number 48 I have here and the command number 49, they are only for the drawing. The 48 will draw the radial line. Sorry, the 48 will draw the name, will add the name to each DMU. Okay, so watch it carefully. It says text. That means that for each input and output, watch the word here, row names. You see, that's why we changed our row names to farm. So use the row names in farm. And when you go up here, farm is this, not farm 1. You see, farm 1 didn't have row names to be the names of the DMU. Farm 1 had the row names to be 1, 2, 3. But farm has the row names to be DMU 1 to 5. So that's what you're going to use. So you're commanding it to use the row names inside the farm. And then it should call the whole frontier blue. I want to change the blue to black so that, because there are some blues already. And Emily, your pink, it looks like it doesn't pop so well, does it? But it's okay. You see your pink? Do you see your pink yourself? She said yes.
Okay, that's lighter than the rest.
Sorry?
It's lighter than the rest.
It's what than the rest?
Lighter.
It's brighter.
Lighter.
Yeah. So is it okay? Do you see it? Are you okay with it? Of course.
Mm-hmm.
She's okay.
It'll be okay.
Let me run it again. Oh, where is it? Okay. So now let's add the text. Let's call the text color black. So this will put the text on each DMU. So you can see that each DMU has been labeled.
Yes.
Who's done with that? If you are done, just say done.
Done.
So 3 of you have been able to do that. As for Albert, he says he's behind, so for him, I understand. What about the rest? 3 of you said done. Jerry, are you done?
Yes, Doc.
Okay.
I said done.
All right. Now, you can add a DEA line or the radial lines. So that's what you call. Now, remember that this radial line can be changed. Okay. But know the way it is. What do these elements mean? Now, if you check carefully, you will see that the lines here, I have X1 for the first one. So X1 has got the line, and the X2 has got the line. So if you're using different lines, you have to be aware and note that you are using different lines. That is very, very key. And the lines we have dotted, I've made it dotted. Which means that if I don't make it dotted, there are other ones I can do apart from it being dotted. So what are the alternatives you can have? Emily. And by the way, anytime you don't know some of these things, use the AI chatbot or something to guide you. But there are several ones. We have the dotted, we have the dashed, we have the dot dash. We even have the long dash. And we also even have 2 dash. So let's run the first one, the dotted. So you can see that now you have all the radial lines drawn. If I change the data set and I tell you to do all of this in R, you should be able to do. Okay. I forgot. I can stretch it like this and it will be even clearer. But that is the key. All right. So that's all about the graphing. Okay. Because we are going to do radial for each one of them, I left that. Now we can go ahead and estimate the efficiency score. Both the technical efficiency score and the technical efficiency score under the CRS, as well as the technical efficiency score under the VRS. That's what we are doing. So there are several ways of the graphing that one can do, but this one's alone are enough. So we are going to estimate efficiency scores now. Now watch here carefully. I said slacks true. So what does a slacks true here mean? Slacks true. It means that you want it to pull out the slacks. So let's run the efficiency score. It's just going to give us the efficiency score. I'm doing it for both. And if you want the result, just highlight the TE constant retention scale. And this is input orientation. That will give you the score for the constant. When you do this for the variable, you get the same thing because you're all in the same locality.
Sorry.
So the constant and the variable are the same. I bet you are talking.
Oh, sorry, probably yeah, my internet was breaking. Apologies.
Okay. Now this next one shows the summary of the efficiency scores. Watch it. The summary of the efficiency scores. Now, if you are running cost efficiency, dynamic efficiency, or anything, this part here is where you will change the coding. So you got to think about how to alter the coding at that stage. You cannot use DEA. You cannot, when you're estimating, you cannot use, you see this code here, I have it as DEA because I'm using benchmarking, don't forget. If I'm using DEAR package, so there are 5 main packages you'll be using for all the complex models. Okay, but this is the normal BCC and CCR. This is the radial one. And if you want the summary of the results, you can use this command to get a summary of the results. Okay, so you cut down the summary of the results tells you something. This has given you a complete summary of the entire results. What are some of the importance of the information you are getting here? Now, please note that this is DEA, and we are using benchmarking. And benchmarking doesn't do non-orientation. Take note. Benchmarking software here, it doesn't do non-orientation. There is a way it calls it. It calls it input and output. And then it also calls it a graph. So the various orientation can be in those formats. The graph is a hyperbolic, not a straight line. So the graph efficiency one uses a hyperbolic measure, which is nonlinear. Okay. So that is how we don't use input and output for that purpose. Also note that the retention scale that we just gave, we have chosen the retention scale, which is constant returns and the variable returns. You see that here, constant returns, variable returns. But the other ones, we have the FDH, which is the free disposal haul. We have the DRS, the IRS, the additive. The additive is there. So I can go here and change this retention scale and say that I want the additive. Okay. Now, if I go, it would have used additive for the score. And you can see that additive, you see the scores I'm getting. The additive will give you many, many efficiency scores, as you can see. The only one that is not efficient is DMU1. And there's no surprising because it goes far away from the frontier. So that's what additive will do. But We don't want that data. We want the CRS, so we just go back. And then we institute the CRS. Okay. So, what are some of the things the summary tells you? What are some things it gives you? The summary. What are some of the things it tells you, at least?
Then I think it's understand that it tells you the number
Emily, you are
of
far
efficient
away.
points. But it tells you the number of efficient points.
Okay.
Efficient points are being used out of all of them. So here you have 3 out of 12.
Okay.
And it tells you the mean efficiency, which is 0.81.
Okay. It tells you the highest value of efficiency and the lowest value of efficiency. And then the ranges. So, you see, this is a small data set you know already, so you are not confused. But if it was a very large data set, you will see that this summary is useful. Okay.
Please, question. When you get up to the line 37 with the plot, I can see that the RCS that was selected was CRS. The graph that came out was VRS.
The what that came out?
Okay, so the one we want to get the frontier, that's line 37.
Line 37.
No, 37.
Okay. Uh-huh.
Yes. It gave us the VRS frontier.
How do you know that this frontier is VRS?
Then because the CRS frontier starts from 0 and then just moves outwards.
The VRS frontier does not start from 0.
Yes.
You said that it has given us a VRS frontier, even though I use a CRS.
Yes, Doc.
Yes. And I'm saying that in an input case and in an output case, you don't see the frontier. You are not able to distinguish the frontier as VRS or CRS.
Okay.
When you are doing input graph and output graph, you can never tell whether the frontier, you can never tell whether the frontier is C or VRS. But when you are doing input-output, do you get it?
Yes, Doc.
Yeah. Input-output, yes, that one you know the frontier. So if I go and use VRS here, I'll still get the same frontier look. It does not distinguish the frontier when you are on input-oriented graph or output-oriented graph. But when you are on both input and output-oriented graph, yes, you get the frontier will be distinguishable. Jerry, do you understand?
Yes, Doc.
What do you understand? What do you understand, Jerry?
Like how to identify whether the graph is an input oriented or output.
You have to identify whether the graph is what? Input or output oriented.
If it's an input oriented or output oriented, you will not be able to distinguish between the two.
Yeah. Unless it is what?
Unless it's non-oriented.
Very good. Okay. So now you can show the efficiency score, but it's better to print the efficiency scores. So you can see that in my command number 56 here, I'm going to print the efficiency score for the CRA. Please watch the way you label it. If you check carefully, I am calling this, I can change this name. but I'm calling it technical efficiency score under CRS. It should be equal to technical efficiency score dollar efficiency. So watch the way I've given it. Okay. That is how it will be. And the digits here means I want you to use only 3 digits. If you check the original results, it was using 4 digits. 4. But I want you to use 3 digits. And it will also print the results in a vertical order. So using print is very important. So you get the results written nicely like this. And you can easily export this to the Excel. Okay. We can do the same thing for the variable retention scale. And for that variable retention scale, I can, in fact, I'm not going to do this one. I'm going to just add the 2. So you can see that now I do one for the constant, do one for the variable, all with 3 digits. So when you run this command, you get them nicely done in a vertical fashion, nicely packaged. And in this very example, because the output has been normalized, the input and output orientation, you are going to get the same score for VRS and CRS because they are all located around the same value, the same region. Okay. The next thing is that you can plot the efficiency scores using a kernel density graph. Now, guys, this is very important. Okay. You can plot the efficiency using a kernel density graph. Now, there are 2 things I've done here. Okay. If you check the first one here, you see, what I'm about to show you is very important. I'm going to go back here and type. I can now, instead of writing digits equals to 3, I can say that I want you to give me the rounding of the efficiency score. I want you to round the efficiency score, put it into a data.frame. Okay, a data.frame. And inside a data.frame, you can pick all of those things that are already inside this. Everything that is already inside up to here. You can drop it after the frame, do a comma and add 2 or 3. You will get the same thing as the one I just did. But you see, in this case, you have it very nicely packaged. Even if I make it 2, a 3, the same 3 digits, it rounds them equally like the one we did before. So I just want you to know that there are 2 ways of looking at this. Either you are using the print or you are using the rounding of the data frame. Okay. Now let's go to the efficiency density plot. What's that? What's a density plot? So I'm going to do a density plot of the efficiency. Now, if the efficiency scores are equal to 1, most of them are 1, you will see that the density will peak at 1. But what is that density plot? It's called kernel density. You know, it measures the efficiency considering them to be between 0, bounded at 1. Okay. So if I run this one now, it shows efficiency scores. It is very, very multimodal because some of the efficiencies are below, some are above. You can see that in this example, we know that the lowest level of efficiency here was what? Who can tell us? What was the lowest level? What was the
The
lowest?
lowest was 0,
0.5.
I think 0.5.
So why did the graph not start from 0.5 somewhere here? The graph anticipates potential efficiency scores before the lowest. That's it. It's a distribution. It's a distribution. So take note. Now, at which point of the kernel density graph would there be the highest? Would there be the highest density? Remember that this efficiency score is based on something we call reflection method, Silverman reflection method. And it uses a default window kernel and a default bandwidth. The bandwidths are the window weight. No. They use that in the method of the density. So take note. So in this case, there is something why the efficiency score is peaked at 1. Who can tell me why? Why is the density highest at 1? Unlike any other place.
Doc, I think because our data, 2 DMUs had an efficiency of 1.
Good. Now, if 2 of them had an efficiency of 0.5, like DMU1 and something else, what would have happened? And you still have this 1 here. What would have happened?
And would have had a double bulge.
Exactly. You would have had a double, or bimodality, pure bimodality. And the bimodality will all be at the same density. But in this case, there is a high probability mass only at 1. There is a high probability mass only at 1. That is why 1 is having the greatest of density. The density is higher at 1 than it is higher in other places. It's important you understand this so that when you are comparing density, because it's good to compare density plots than other plots. Okay. So we can now go ahead and estimate you see, you can do the density plots for the VRS. It's going to be the same thing. Okay, so this is a density plot for the VRS. Okay. And there are some beautiful ways of plotting the density, to be honest. Okay. For example, you can also use this command, and then it will also give you the density, this time by restricting the bandwidth. This one is like it is forcing the efficiency score. But even though you have it like this, if you check carefully, okay, it kind of puts everything towards the normality. Sort of trying to put everything towards the normality. So this particular aspect of the density plot, can be used, but normally it's the first one that we use. But this one is when you want to plot the density in a form of a normal density plot. You're forcing it to be in a normal density plot. There is another way of looking at the density. You can have density like this. This one is similar to the first one that we had. And then you can also install, the one I'm about to do is a very, very proper general one. You will install the Gym plot 2. Okay. I have installed it already, so it's already. Then after installing it, you can plot this one, show a line width, and the most important one is the rag jitter. Okay, I'm doing it for VRS efficiency score, but rag jitter is going to show you, where is that? You see the rag jitter? Check carefully at the bottom. You will see some lines. And in this case, check carefully, guys. The lines here, I'm not talking about the lines below the horizontal line. I'm talking about the lines above the horizontal line, the vertical lines above. How many are they? Check it carefully. How many are they? Sorry?
No, 4.
There are 4 vertical also.
There are 4,
No, there are
but they are supposed to be what?
5.
But they are 5, isn't it?
Yeah, there are 5. The one has one on top of it.
Yeah. Not that it has one, it's been deepened to showcase the density. So that is why you read the density. Okay. So it's telling you that there is a lot of density at one. So that's why one is deep. If you have a lot of efficiency scores, a lot of observations, you will see that the density will be matched at where the lines are plenty. Okay, so this is a very good one, okay, of helping a person to know. So even though we have drawn it like a normal distribution, which is what it is, the density is shown in this regard. Now I can still take this rag jitter, okay, take it to the original one that we did. Was this the original one? This one, okay, and just add this to it. Okay, it doesn't accept because it wants you to complete it. Yeah, it wants you to complete it. But so that's what the library ggplot will do. So this one is the only one that can do that. Oh. Very good. So here you have that density there. I think at this stage it's split a little bit. Do you realize I split a little bit above 1?
Yes.
But that's okay. The key point is that the rag jitter will show the strength of the normality. This is another one called density plot. It doesn't normally show that it's normally distributed, so it doesn't really work well. Then there is a ggplot geom. I like this one, because I like it. It doesn't show it here, but it gives you a very nice shape of the density. I don't know why it's not working here. A very nice shape of the density of the efficiency scores in a way that it is a bit colorful. It said it's like it's aesthetic. It didn't show that much, but it is one of the things that one can actually do. So I mean, there are quite a number of them. You should just familiarize yourself with them, and then you can get a bigger picture of that. So which one were you able to do? But the key point is not just the doing of the thing. The key point is the interpretation. Interpretation of the thing. That is more important than just doing the thing. And we have only 5 firms, so it's always good to know that it's best to have the density. It's best. It's best to have the density plot. Because when you have the density plots, it gives you a picturesque understanding of the whole work. A picturesque understanding. Let me try this one and see whether it will work. Okay. So that we can say that, because this very one didn't work. So let's see. It might.
Doc, the number 71 also did not work.
71, I've already indicated that it's not normally distributed. I don't want to use that one. So let me drop that one.
Okay.
But this very one, I don't know why it's still, I mean, sometimes it does give you the results, even though, let's see, even though, no, it's not. Let me try this again. I mean, it's good to fidget with some of these things so that you have a very beautiful density plots. No, But here I use, I think I'm using a different thing. It's supposed to be that. Supposed to be this.
Doc, I think you're using gin instead of farm.
That is true. Well, then I need to even change the others. No, it's supposed to be inside efficiency. I won't lie to you. Anyways, the gene is still wrong though. It's supposed to be. Anyway, so fidget to them and then get some of the interesting things about, because I wanted a very nice one, but the best one is always the one with the.
Okay, Doc, please, mine worked.
Okay, so give the code there on the page and then let's see. It's good when it works. Put it on the charts and let me see. The rest of you, did yours work?
Yes, Doc. After we changed from gym to farm, it worked.
Emily, where is it? Where have you put it?
Doc, sorry, just a sec. I posted it at the wrong place. Okay, Doc, on our page.
Yeah, I've seen it. Okay, so like I said, you fidget with it and then it works. That's it. You fidget, it works. Perfect. So this is another way of looking at it. Now, the beauty of this one is that you see that the jitters are still at the bottom. It still has the jitters. And you can see that it's starting exactly at 0.5. Do you see that? It's starting, yeah, it's starting exactly at 0.5 and peaking, almost at 0.9 towards 1. Because apart from the point, you see, when you check the efficiency scores, apart from, let me just show the one that has a printout. If you check carefully, even though you have 1 and 1, the other one is 0.3, 0.83, and 0.74. So there is more movement towards 1. There is more movement towards 1 than 1. But then if you check the other ones, they are also driving the thing. So there is more concentration at 0.9 thereabout, or a little above 0.9, if you check what I mean. That is why there's not much, well, there is concentration at 1, but then it's not just the number it is picking. It's picking the concentration, even between the numbers. So that is why you see it like this. But that's good. So this is how it's supposed to be. Then we go to the next part, which is key. The next part is the peers and benchmark. So who are the peers and who are the benchmark? So first of all, the peers are for you to be a peer, you've got to be a real DMU. That's one. You also have to be an efficient DMU. That's it. So you got to be a real and an efficient. We know that they have the efficiency score of 1. So obviously it's going to be DMU 2 and DMU 5. But who is using them as their peers? So when you run the peer analysis here, you get this. Okay. So there are 2 peers. That's what it tells you at the top. And it tells you that the first DMU1 is using 2 as his peer. He is not using 5 as his peer. The second DMU is using 2 as a peer, not using 5. Okay. The third is using 2 and then 5. The fourth DMU is using 2 and 5. And the last DMU is using itself, and not the other one. Of course, you notice that the second DMU is also using itself. So it tells you the peers, and then you can also count the number of times a firm has been used as peer. Now, this is just 5 DMU, so obviously it's easy to dictate that, 2 was used 4 times as a peer. You can see it here. And 5 was used what? How many times?
3 times.
3 times. So you can see that, but if the firms are many, you can't do that. So there's another command you can use, which is the next one here. Get me the number of times the peers were used as peers. So once you write this, okay, once you write this, you are able to use this very one. You're able to use this very one because this one tells you that how many times was 2 used as a peer? 4 times. How many times was this used as a peer? That. So in an exam situation, for example, you will get some of these things for you to make sense of that. Okay. And then you can now say, who are the peers of this one? Sorry, who are the firms that this particular firm used as a peer? If you want that command, you can use this which command. So if you take DMU5, and this one shows that it's DMU5, DMU5 was used as a peer by who? By itself. That's the first one. And by 3 and by 4. But you can go and change it. Because here, what I did was, I did for 5. And I can do for 2. Okay, so let me run for 2. So you see here, I changed this 5 to 2. And you can see that L2 is telling you that DMU2 was used 4 times, or it was used as a peer by DMU1, 2, 3, 4. Now, if I go and change this thing and write 3, you just watch. 3 is not a peer. So watch it. If I do 3, we'll say null. Okay, because 3 was inefficient. It was not a peer. Okay, and therefore, you can see that it is saying null. Please, you guys get me?
Yes, Doc.
Now, this one is easy to count with your eyes, but like I said, if you have 33,000 firms, you can easily count with your eyes. So you can do a whole lot of peer analysis. That's my point. You can even write a paper on just peer analysis. Okay. Now, let's go to the substantive matter and the key one. If you check, we can calculate the slacks. Now, who can tell me the slacks and which firms have got slacks? Who can tell me slacks and which firms have got positive slacks? Okay, first, what are slacks? Don't give me, give me a practical explanation of slacks here in this context. What are slacks? Those of you who haven't been talking. What are slacks?
Okay, Doc, slacks are inputs used that were not supposed to be used. And so if we look at the DMUs that we have, the inefficient ones are the ones that are going to have slacks because they could have reduced their inputs but did not.
You mean are the ones who are going to have positive slacks, be clear?
Yes, Doc. They're the ones that are going to have positive slacks.
Why? Why?
Okay, that's because inputs could be reduced or can be reduced. So they use excess inputs in their production.
All right. And guys, this is an important point for those of you who are doing SBM. What we are discussing here is very important for you. Anyway, so first let's calculate it. So the slacks here are the unused resources. Okay, the unused resources, because you are doing it input-oriented, unused resources by a particular DME. But those that have used all their resources, their slacks are going to be 0. Okay. So let's run the slack. The slack here is for both the input and the output, as you can see here. Please remember that in real life, you can be doing an input orientation, but the output will still be slacks, will have slacks. Emily, do you get what I mean?
Yes, Doc.
You can still have an output slack in an input orientation, even though you are not maximizing the output. Even though you are not maximizing the output in the input orientation, you will still have output slack. It will still tell you to go and cut down the slacks of the output. Why? Graphically, can tell me why. Graphically, why? And this is why. If you have this one here, and you have, input oriented and output oriented, both of them, okay? Okay. So here, I am here and I'm going to do input orientation. Input orientation that I'm going to do implies that I should reduce the input to the left. Okay. But when I did, I hit on the free disposability section, which means that the input has been reduced all right, but now I need to do what to the output? I need to increase the output before I can be properly efficient. So in this case, we are doing input orientation, but then the slack is on the output side. Okay. How do you clear this thing? Okay. So that is how this can be executed. So if you check this slack, so let's run the slack analysis and then show SL. It will tell you for all the variables, which ones have got slacks. And in this case, it tells you that DMU 1 has got slacks, a slack of 0.5 unit. Now, of course, we knew this graphically. But you see, when I put a big number of data set together, you will know that. You will know that graphically. And so you have to understand the results that are coming. The problem with this thing is what? The problem with this slack analysis using this code is what? It doesn't tell you what. It tells you that there is a slack at the DMU level, but it does not tell you whether the slack is coming from the input side or is coming from the output side. Or even on the input side, which input? And if there are many outputs on the output side, to which output? It doesn't tell you. Okay, but it's a good start. Okay. It's a good start. There is another one, but you see, inside this one, you can calculate more. For example, inside this, after this slack calculation, you can say that I want you to tell me the slack on the input side by typing this. So now you've given me the slack, all right, but give me the slack on the input side. I'm typing this so you guys can follow me. So once you do this, you run it, and then it will give you the slack on the input side. You see, now it is telling you specifically X1, whether there are slacks, there is 0. X2, the slack on the other input, yes, there is 0.5, but is a second input for DMU 1. Are you guys with me? Jerry, are you with me?
Yes, Doc. Doc, I'm here with you.
So what does this result show? This result on your screen, what does it mean?
It means that DME1 has a slack of 0.5. DME2 has no.
But then the first one, what was the issue with the first command, the SL alone? This SL alone, what was the problem?
It didn't indicate which of the input had a slack.
That's it. All right. Now the same thing you can do with the output. So if you want the output, select do SL $SY. $SY. And then when you run that, it will tell you which output. Okay. And then when you know which output, which one is carrying slacks along. Of course, in this case, the output were just one. So take note of that a lot. Next, we can find the scale efficiency because we have already defined the scale efficiency to be the technical efficiency under CRS and then the technical efficiency under VRS, the ratio of them. So once you run this, you get the scale efficiency and then you can highlight and show the scale efficiency for all of them. So you see that this one is telling you that scale efficiency is 1, which means that what returns to scale is operating at the firm level, at each firm level. Which returns to scale is there? You don't know. Emily, you don't know.
Doc, please. I think there is constant return to scale.
Why?
Doc, if it's 1, that means that both constant and variable are the same. So there's no difference between the two.
Should I ask you a question? Say no.
Yes.
Okay. If it is greater than 1.
If it's greater than 1, then it means that constant returns efficiency is larger than the variable returns efficiency.
So what returns to scale is operating?
Then that will be variable returns to scale.
No. This is at the firm level we are talking about.
Okay, firm level. Okay, so for firm level, then that will be increasing returns to scale.
What?
Doc, that will be the NIRS.
No. Go and find out because the thing is that I mentioned it the last time. It was in the previous lecture. So you can now find a complete data frame. I'm not going to do the 86. I'm going to run the 87, which contains everything in the 86. So we are going to do the complete data frame. Now here, I'm going to pick it's everything here. Okay. So you put the data set into, in fact, normally in an exam, this is what I'll put down in an exam. I'll put this down in an exam and then you ask you a series of questions. So here, you'll be able to know the efficiency scores for each firm. You'll be able to know the slacks, whether it's input or output slack for that firm. But in some of them, I will now delete the efficiency scores. So if I delete the efficiency score for DME2, okay, and then I ask you, if I delete the efficiency score for DME2, you don't know that is 1, no? And I ask you, what will tell you that DME2 has is efficient? What will tell you that DMU is efficient? It's not clear here, isn't it? It's not clear. You cannot say that because the slacks are 0, it's got an efficiency score of 1, because inefficient firms also have got slacks of 0. So it's not.
Doc, please, if the peers were there and then they had no peers, can you base on that to say they are efficient?
Yes. So you need the peers and the lambdas, which is the next one we are going to. Okay. So let's start with the lambdas. So we are going to do the lambdas, and you use this command to generate the lambdas. So let's do the lambdas here. So now we have the lambdas. Okay. You have the lambda for DME1, and it tells you that for DME1, he's using DME2 as his peer and DME5 as his peer. Therefore, and you can see that he put all the weight on who? On DMU1. No weight was put on DMU2. No weight. Not a single weight was put on DMU2. Hope you guys understand what I did. Because remember that the weight are the lambdas are the weight of the peers for each firm. It tells you the relative importance. How important are you, firm A, to me? Okay. And he's telling you that you, DME2, you are important to me 100%. I'm not sharing your importance. DME5 is a great, but it's not important to me. He give it 0. DME2 says that he himself is more important to he himself than any other firm. So all the weight on it was what? 100%. But when you go to DME3 is saying that I see some importance of DME2 towards my gaining efficiency. I also see some importance from DME5 towards my gaining efficiency. There, I see 67% importance from DME2, 33% importance from DME5. This is it. This is what I see. So it puts more weight on DME2. Then you go to DME4. He swaps them. He says, no. DME5 is contributing 51% than DME2, which is contributing 43% towards my efficiency. Therefore, I see both of them as important, but one is more important. DME5 says, nobody is helping me. I am my own champion. 100% of the weight is on me, myself. I don't need anybody's help. So if you have like 30 firms, you should be able to look through and be able to deduce all of this. Now, let's go to the substantive point. Okay. Now, you will notice that inefficient firms have got positive lambdas. Now, let me put it this way. Inefficient firms don't share, they don't share their thing with anybody. I'm now going to run the analysis, and then I show you some 2 important things. In fact, there are 2 important things here. Let me just bring this one here before. But we need to calculate target. So let me talk about target first. But the targets are what I will actually let you calculate in an exam. But here I'm calculating for you. I'm calculating for you. But in an exam, I will leave it blank for you to calculate. Take notes. But first, let me just show you. So a target, watch it. The definition of a target is very important for you to understand. You can, let me just go to the slides here. You remember the last time I told you that there are 2 ways of finding the targets. What are the 2 ways of finding the targets? In fact, what are the 2 ways of finding the target? Do you remember I said that?
Yes, Doc.
What are they?
I think the first way was multiplying the efficiency score with the score of the DMU you are considering.
Good. So the first approach is using the efficiency score. The second approach is using the lambdas. That's what we said. Okay. So here, now coming back to this table, as you can see, if I should delete this one here, what do you call it? if I should delete this one here, what will indicate that a particular firm, if I delete efficiency score here, okay, what will indicate that a particular firm is efficient? Suppose you didn't know that DME2 is efficient. What would tell you that DME2 is efficient? Two conditions. What would tell you that DME2 is efficient?
Okay.
Doc, I think it's showing as one of the PS. So it's showing as one of the PS up
Exactly.
there. So L2 and L5.
Exactly. It tells you clearly that it is one of the peers, L2. So therefore, DMU2. But you see, it won't come into the mind of somebody immediately. You know that. So if I were to tell you that and if I had deleted that shaded area here, and I said, what is the efficiency score of DMU1? I will not ask you, I'll just say, what is the efficiency score of DMU1? You must remember and know that since it has been used as a peer, its efficiency score is what?
One.
Yeah. You must know. Not your father, not your mother, you. Do you guys get it?
Yes, Doc.
Okay. So that is a clue there. Okay, now let's go to the target. How do you find the target for DMU3? Because if I tell you how do you find the target for DMU2, you will just come and because you know it's efficient, you just calculate this. And so the input X1 target is 1 and the input X2 target is 2. You're done. Okay, because it's efficient. You just use your actual. But then I ask you from here, how do you find the target for DMU3? What will you do? What will you do what will be the target? Because now the target is not shown here. How will you find the target? The target X1 will be equal to what? The X1 for this DMU3 will be equal to what?
Doc, S1 for DMU3 will be equal to 0.667 or 0.67 times 2 plus 0.33 times 2.
That is correct. I hope the rest of you saw that.
Yes, Doc.
Good. Let's look at the X2 target. I want the X2 target for DMU4. The X2 target, not the X1. How will you calculate it?
Doc, is it 2 times 0.57?
No. What would be the X2 target for DMU4? You have to take the 2.
Okay, Doc, that one will be 0.428 times 2 plus 0.57.
Where the 2 is coming from? Which times 2? Which 2 is that?
Doc, the 2 under the X2.
The 2
for DMU4 under the X2.
Are you multiplying it by the 2, the DMU4's 2?
Yes.
No, but you can't do that. You can't multiply by the DMU4's 2.
Okay, so Doc, that one will be 0.428 times the 2 under X2.
As the 2
for
under what?
DMU2.
Exactly. Now you're talking.
Yeah. under
The
X2,
two,
and then
the DME 2 under X2.
yes, and then 0.571 multiplying 1. That's the X2 under DME5.
Now you're getting it. It's important, guys. We went through it. It's important. It's not just important. It's extremely important. So let me just take you back here. So the target for this one, the first one, is 0.666 for DMU 3. This time I'm doing for DMU 3. The next one will be that 0.666 times 1. Now the 1 here, and if you can remember, the 1 here is that 1 for DMU2. Okay. Is it? No, that 1 for DMU5. Okay. This is that 1 for DMU5. Then 0.333 times the 3 for DMU5. So that's it. The definition is here. You have to take it, sorry, you have to take it for here you have to take it, the first one is for the DMU2, and then the first one here is for the DMU5. So let me take it out. You don't have the input and output here. But when you take, let me see whether I can copy this and bring it here. Yeah. I just brought the thing here. So this is it. Okay. This was the input and output we just had up there. So when you check it carefully, and we are just trying to calculate, for DMU3. So if I want DMU3, because we are saying that these inputs, the inputs that you are seeing here are not good. Okay, these two are not good. They are too much. So we need to bring them down. So you got to take the lambda for 2, and the lambda for 2 is this one. For that DMU3, it is 0.666. You have to take this lambda here, okay, and multiply it by DMU2 input. A DMU2 input here is 1, okay, and we are doing it for these two here, okay. We are doing it for these two. We said this is too much. Then plus this 0.3. And then you also multiply that 0.3 by DMU5 3 here. And that will give you, they're all under X1. And that will give you the X1 value for this one. And that's what you have here. So it's the lambda of the second pair multiplied by, but if the pairs were 3, you would have gotten 3 different, lambdas. Okay, so you have lambda 2, lambda 5, maybe lambda 7. And now you have to take each one of them, multiply, and then sum them up. I think you guys get what I mean. Do you? Okay.
Yes, sir.
Learn how to do this computation. Learn how to do. You will compute this. Come hell or high water, you will compute this. So learn how to do that. Now, let me just delete it. Okay, so that calculation is here for the first one and is here for the second one. So there were 2 for DME3. They will all have to be brought down to 1.67, 1.67. That is when you know that is the target. So it tells you that 1 and 3 and then 2 and 1 are the inputs of DMU2 and 5. Those were the role models of the DMU3. Now, when you go back here and you want to calculate the target graphically, tabularly in R, the target is calculated as the efficiency score. Watch it carefully, because here I use efficiency score. Efficiency score multiplied by the input for each DMU, its efficiency score. So it's like I'm taking this efficiency score multiply by the input of the DMU, okay, minus the slacks. Minus the slack. So if I want to get a target for this X2, I take this efficiency score, which is 0.5. 0.5 times 2 is 2.5. Okay. Then I take out the slacks. And the slack for that is what? When I come here, the slack for this is 0. Okay. The slack is 0. So now let's take the efficiency score. The efficiency score is 0.5. 0.5 times 2 is what? 1, isn't it? 0.5 times 2 is 1. Then you subtract slack from it. Guys, pay attention here. You subtract slack from it. Now, the slack for this is 0. If you check the slacks for X1, X1 slack is 0. So it will be 1 minus 0, giving you what? 1, giving you the efficiency score. Okay. Now, the same way, if I want the efficiency score for this one here, 5, see 5, this one is 5 there, X2. I still multiply the 0.5 by 5. That will give me what?
2.5.
That will give me 2.5. Okay. Then I go and subtract the slack. When you subtract the slack from it, what do you get? The slack is 0.5, so you get 2. So it means I've got to cut down this DMU2 up to 2. So using the efficiency score, I can use that principle to calculate the slack. So I'm going to run this and then add it to the model. So when you run this and now finally add it to the model, let me squeeze and create more space. You will now be able to find the slack. Oh, sorry, the target for each. Oh, where is the target here? Okay. It's supposed to show at the top somewhere. Okay, it doesn't show here. Oh, yeah. It's this one. It didn't call it target. It called it X1.1. Okay, that's the name it gave to it, S1.1. Let me see if I use, I don't know if I use EFF there, it will work. Let me see what, I don't think it will work, but let me just try and see. Yeah, I know it will not work. Okay. So it will give it a new name, and you just have to know that that is what target. So you can see that truly what we calculated, the target for the DME1 is actually 1 and 2. That's the target. And the one that we hand calculated is this one. That is also like that. So when you want to do graphical analysis, practical analysis, you can generate everything. Look, this is a complete analytics of everything that one can have for everything. And you can do a very, 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 very managerial analytics for all of this. Everything that you need to make managerial decision is here. But what I'm saying is that this last 2 columns, I will not give it to you in an exam. Okay. You would have to compute it using the 2 approaches. Now, let me just warn you with something. Do you know that for output efficiency score, the score is above 1? You know that? So that one, when you're calculating the target, should it be reduced? Should the inputs be reduced, or should the output be reduced or increased?
Look, they should be increased.
Okay, so because they should be increased, the way you calculate the target will be different. You are still going to take the efficiency score here, multiply it by the output, but you will add the slack. Take note of that. You are adding the slacks to get the target, the output target. Because they were all thinking about input a couple of years back, and I changed the question to an output, then all of them failed. And when you go to the other one, when you come here, okay, you can see that here for the same one, you take the lambda values and multiply the lambda if you want to get the target for the target approach, for the lambda approach. You multiply it by this, add it to this one, and then you so multiply. That one is cool. But after that, you have to also go and what? Subtract the slack. You still have to subtract the slack from here. Okay. You don't stop here. Do you? Yes. You have to subtract the slack. If there are slacks. Check. Well, in all of them, if there are slacks, you have to subtract the slacks. Sorry, did I say you have to add the slacks for the output oriented? For the output oriented. So know how you calculate the output oriented. I have some past questions on that. Okay. So now we are done. We are just left with two things, and then that will be it for the interpretation. You can calculate how much input could be saved. Watch this word. How much input could be saved if all the firms were efficient. Right now in this industry, okay, how much input could be saved? It's like asking the managerial question that how much of deposit could have been collected in this banking industry if all the firms were efficient? If they were efficient, the amount of deposit mobilization in the Ghanaian banking industry, what would it have been? In this input orientation situation, okay, if you calculate, you're going to have this. Okay, so for each one, you see here, you're getting the target. You're getting the target for, sorry, you're getting, what do you call it? You're getting the input saving potential for each one. Okay. Now for DME2, because it's efficient, there's no input to be saved again. For DME5, because it's efficient, there is no input to be saved. Okay. But for DME1, there's a lot of input, both on the X1 input and the X2 input. There's a lot of input that could be saved there. And for DMU4 too, there's a lot of input that could be saved there. Okay. But that is, for each DMU and each input. What about if you want it all in percentage? What is the total sum, okay, of input that could be saved? This is it. So if you calculate, so first of all, you are going to get this total amount of inputs that could be saved. Total. It's like I'm adding everything to this. I get 5.595 inputs. Okay, but that one doesn't make sense. Let's get percentage savings. Okay, you multiply that by 100 and divide. The percentage that could be saved is this. So 24% of input could be saved should every firm had been efficient in this industry. And you could see that a lot of savings would have come from DME1 because DME1 is suffering. It's suffering a lot. A lot of that could be done. And that is how you execute this analysis. So you can see all of the analysis. The percentage that could be saved is 24.33. So this is how you can estimate the DEA approach and everything, every possible things. These slacks and all of that will be clearer when we are doing slack analysis. Any question?
Doc, please, what you just explained, I wanted to find out the percentage of the savings. Can we look at it in terms of what individual DMU would have saved?
Yes.
Instead of a single score.
Yes. So all you have to do is to take this one here and then go to each one of them. So when you go to each one of them here, you take, if it is 1 for DMU1 here, you take that 1 divided by the 5.59 multiplied by 100. So you will know how much it will be saving in that input alone. But if you want to combine the two input here, it will be 3.5. So you take 3.5 divided by 5.595 multiplied by 100, and you will know how much input that particular DMU could have been saved. Yeah.
Thank you.
Any other question? So the analysis is very, very important for you to work it out every single time, understand the analysis, understand the analysis. Okay, let me take you back to the next step. So this is how benchmarking can do the work. But remember that you can also use FEAR, Frontier Efficiency Analysis in R, or DEA, okay, packages. You can also use them a lot, especially when you're doing the bootstrapping. They are fantastic. Okay, now let's go to scale efficiency again. We've looked at a little bit of information regarding scale efficiency. All of this, you looked at it in terms of, but I want you to take note of this, Emily, because of the point. I told you that when the efficiency score is bigger than, hey, I changed the distance. Okay, yeah. But when you use the DER, it becomes easier. When the efficiency score is bigger than 1, and I want you to check here. Okay, when it is bigger than 1, the firm is experiencing decreasing retention scale. Now, I want you to understand that when scale efficiency is bigger than 1, it means that you are too big. Take note. It means that you are too big. Too big are those who are experiencing decreasing retention scale. So decreasing retention scale means that you are too big and you got to come down. Increasing retention scale means you are too small, you got to go up. Keep that in mind. Okay. So scale efficiency being greater than 1 means you are too big, you got to come down. So it means that the firm is experiencing decreasing retention scale. And there are other ones. All of these ones, we looked at them the last time that we met. We looked at each one of these. And we can now go and do retention scale at the firm level using this R, but we have to use the DER. Okay. So we can proceed here and do that. So if I were to go down here, let me just create some space here. To do that, you can follow me. You have to do library. Oh. You have to do library.
It's the PowerPoint that is showing, not the.
Oh. Is it better now?
Yes, Doc.
You have to do library into bracket DEAR. Okay, that's this one. Now, if yours doesn't come, it means that you have not installed it on the package. So go to packages, click install, and type DEAR. If you run your library and it doesn't show down, okay. If I run my library, let me run my library. It shows down here that it's been done. It shows clearly that it's done. Okay. But it also mentions that it's been matched from the following packages. Sometimes you have to continue. Sometimes you have to just restart to start using the DAR. It doesn't matter which one. And then you can go up there and then install your data. Bring back your data. Okay. I'm bringing back my clipboard data. That's what I'm doing now. So here, I just loaded the data set. I just loaded the same farm 1. So if I click farm 1, the data set is nicely showing down here. So you should also load your data set. In fact, I don't have to load it because it's already there. Then let's call this example EJRTS. Okay. So let's say example RTS equal to. And then we have to convert the data. That's the next important thing. So equal to read underscore data. Read underscore data, and then put into brackets the name of the farm 1. So you call it farm 1. And then you do a comma. Then you indicate what are the number of inputs. In this very example, the number of inputs are 2, X1 and X2. Then you do a comma. What are the number of outputs? The number of outputs equals to 1. So you also do that and run it. Okay. Now, to give you some warning signs, but don't worry, keep going. Then you go to the result. So let's say result R equal to. we run the model. We're going to run the basic model. So let's do model underscore basic. It should be somewhere here. Model underscore basic. This one. Now the basic model will run the normal DEA model. So model underscore basic. Then into bracket, you pick the name of the new data set, which is EGRTS. I just picked that. Then you type your orientation. And then you indicate your orientation you are using. You bring the double apostrophe and say input orientation, IO. Input orientation. Then you do a comma, step out, do a comma, and do RTS, returns to scale. And the returns to scale, you also put that in double apostrophe and type constant returns to scale. You can also do variable, it doesn't matter. That's it. Run that. And then you go to the last but one, you want to see the efficiency score, so type efficiencies. The moment you start typing, it will come. Efficiencies of what? Of the R, the model you just did. Okay. Do that and run it. And you see that it's giving you the efficiency scores. What I am seeing here is quite strange. Input orientation. I'm not seeing the right results. So let me go back. Those are the inputs. Number of inputs is this. Oh, the thing didn't run. Do you guys get the same values?
Yeah,
Yes, Doc, I got the same thing as you.
Okay. How will I get this sort of efficiency scores? Why will I get that? I'm trying to understand. This is DER. You can always go to the help section here. And model basic. Everything that we did is here. And when you go down, you see an example. Let me see. Basic PFT, returns to scale. The same thing that we had. See, we had the name of the data. I think the slight issue is the name of the data. So let's say, let me pick on this. Let me pick on this rather. Okay, and see whether I can alter it. So let's call it EGTRS. Make data.
Doc, I think I've seen the issue. I tried this. You see, for our data sets, we had the Y first and then the X1, X2, second, and third.
I should be.
When I changed it to, the input should be first before the output. When I did it that way, I got the right scores.
Yeah, that makes sense. So again, it's always good to try and find out what the reason is. Okay. So you go to your data set here, and the way it is, just bring this one first. Because you're going to do input orientation, bring input orientation first. And then output orientation second. It always takes the first one as input. That's the problem. So what it would have even done is I would have taken rather these two as output, as what do you call it? In this example, it would have taken these two as input. That's what it would have done. and rather taking the last one as output. But it's supposed to be this. So thank you for that. So when we go back to here, to the exact data, we don't need to just do this. Just reload the new data set. Okay. Just reload the new data set. Run. And that's exactly what we had for the results. I hope you all have done it. Then you go to RTS, type RTS into bracket R. That is going to give you the returns to scale. When you run that, it will tell you that all of them are constant returns to scale. Okay, which we know is supposed to be the case because we are not using input-output graph for this. And then we also have small firms, all located in the same corner of the PPS. So that explains why we had this result. Okay, so I have an assignment for you to do. Emily, where is the first assignment? I've not seen it.
Doc, we are printing it today.
I need that assignment. Find a way to get it to me. Now, this assignment is for next week. So you have this time an output-oriented. Okay, not the input-oriented that we've done, an output-oriented. And then, well, I shouldn't have said it. And it's even been normalized. Okay, so you have that. And then you say using the data, draw the output transformation curve, determine the VRS scores, PS, targets of our output lambdas, what percentage of output could be saved, use the lambda approach to manually find a benchmark target for B. Okay, use the efficiency scores approach to manually find a benchmark target for B1. How many times was E used as a peer and FEMC used as a peer? How many peers did B have? And which, if any, is a potentially best peer? Why? Okay. Interpret efficiency score of B. What is a mixed inefficiency of J? Compute and compare the SBM score with the BCC score. And in fact, you should also generate your table. Now, remember that if you're finding the SBM score, you got to use the DEAR package that we just used. So do that. You can use just 30 minutes or an hour to get that done. Ladies and gentlemen, that brings us to the end of our meeting for today. Any questions?